perhaps let's begin then by what do we mean by linear differential equation? What do we mean by a linear differential equation? And by a linear differential equation, what we mean is a differential equation so that if you have a handful of solutions, a linear combination is again a solution. That's what I mean by a linear differential equation. So it's a differential equation for which if x1, x2, up to xn are solutions, so is x some linear combination of these solutions. And then as an example, let's do our favorite example. Maybe x double dot plus 5x dot plus 4x is equal to 0. And if we did a little work, we could probably figure out that x1 of t is equal to e to the minus 4t, and x2 of t is equal to e to the minus t are both solutions. So is x of t is equal to c1 x1 of t plus c2 x2 of t. That's what I mean by a linear differential equation. Is that it, like a matrix, if you have a solution to the matrix vector equation AX equals 0, if you have a handful of solutions, you can take a linear combination and get another solution. That is the null space of the vector space. Similarly, if you have a linear differential equation and you have a handful of solutions, you can take a linear combination and get yourself another solution. That's what I mean by a linear differential equation. So let's see, for example, let's look perhaps at an example of a nonlinear differential equation. What is an example of a nonlinear differential equation? Well, it's a differential equation that's not linear.
Yay.
But we're going to clarify that with an example, because that's not the most helpful thing I could have said. And an example that you saw in your reading was x times 1 minus x. X dot is x times 1 minus x. And I'd like to convince you now that this equation is not linear. Are you ready to be convinced of this? Are you ready to offer your own explanation of why it's not linear? Jasmine.
Okay, well, when you do it out, you end up getting an x squared, right? And that's not a line, that's a graph.
So you're saying the function on the right-hand side of this is not a line, it's a parabola. And that suggests that maybe something's going to break down if we take linear combinations.
Yeah.
Charlie?
Greg.
Greg. Greg, sir.
Perfect, all right. Well, we did at the very beginning of the Q unit, we experimented with various different functions and tested whether they had linearity, i.e. whether they were linear. And one such function that we determined to not be linear was x squared, which the way that we decided it wasn't linear, I believe, was by testing c times L of x, or c times L of t was unequal to L of c times t. I believe
Let's do that. Let's do that. So suppose x1 is a solution, and let's let x be some constant times x1. Now, this is I have not written down a formula for x1. I have not written down a formula for x1. I'm just saying it's a function, and I don't need to write down a formula for x1. It's a solution. I know something about its derivative, and that is enough to tell me something about the derivative of x. So let's figure out what's the derivative of x. Who can tell me what the derivative of x is? X dot, great, okay. So x dot, and then maybe in terms of the derivative of x1, what is that? Cx1 dot. And now can we rewrite x1 dot in terms of x1? You got some slow nods, but so x1 is a solution of this equation, so x1 dot's got to be x1 times 1 minus x dot. If I can write. Great. Now, can I rewrite x1 in terms of x? Cx1 is x, and x1 is x over c. This satisfies a different differential equation. It's not the same differential equation that x1 satisfied, it's some new differential equation. And so we don't expect here that x is going to be a solution to this differential equation. It doesn't satisfy this differential equation. It satisfies something different. So this is a nonlinear differential equation. Since you take a solution and you scale it, you don't get a solution back. You get something else. Similarly, if you take a handful of solutions and take a linear combination, you don't get a solution back. You get something else. Nick, has a question.
So they're closed under multiplication and addition, not closed. The linear differential equations are closed, and this is not, and therefore it's not.
Right. Yeah, you can say the solution space of a linear differential equation is a vector space. The solution space of a nonlinear differential equation need not be a vector space.
Okay.
And I'm sort of trying to use both the abstract linear algebra vocabulary, but also ground it in this sort of concrete notion of what the actual operations are. Because I think some of you are really excited about the abstract linear algebra vocabulary, and some of you less so. Is that correct? Yeah. Okay. Is this distinction between a linear differential equation and a nonlinear differential equation, has that distinction been made clear? Yeah? So, while we have that equation up on the board, I'd like to, are there questions? You're too shy to ask questions. I know spring break was a long time. Yes?
I'm sorry, could you go over the last line once again? I don't understand. Did you substitute something in or solve for the derivative?
And so if you take x1, could you use another
Ask.
letter? Because there's a lot of x's.
Pardon you, the preference is to use a new variable like y instead of x1?
Yes.
Okay.
But
I certainly can do that. So what I've done is I've used this relationship that x and x1 are related by the multiplicative factor c. X is c times x1, and so x1 is x divided by c. And everywhere I see an x1, I replace it with an x divided by c.
so where did you get the x1?
Pardon?
Where did you get the x1 in the first?
Right. How best to address that question? I'm trying to furnish an example of an equation which is not linear.
Okay.
And the property of a linear equation is that it respects linear combinations. In that if I have a handful of solutions, a linear combination of those solutions will again be solutions. So to probe whether or not a differential equation is linear, what I need are a handful of solutions. And I'm going to take a very small handful of solutions. I'm going to look at just one solution, and I need to give it a name. So the name I've chosen for that solution is x1. Have I addressed your question? I feel like I have not addressed
So
your
like
question.
in this case, if I like refer it back to the other example, you're kind of in some way. The
Mhm.
next one you're saying is the solution which was represented in the first equation with e to the negative 14. I mean, c.
Over here, I happen to know what the solutions are, so I can write down formulas. But yeah, so here, let's say I found a solution, which was e to the minus 14.
Uh-huh.
I can do things to this solution. I can multiply it by constants. It's still going to be a solution of this equation. But here, if I multiply this solution by a constant, it's no longer a solution to the equation.
And maybe it's worth saying that Professor Hoffman doesn't necessarily have that solution. For this problem, he could figure it out. But you don't need the solution in your hand. Notice the word is suppose x1 is a solution. So if I had a solution, which I don't have it, because I haven't been able to figure out how to get it, but if I had it, then I'm going to look at a multiple of it, and boy, a multiple of it isn't a solution, so that tells me my differential equation wasn't linear. So I don't need the solution in my hand to be able to do what Professor Hoffman did. Does that make sense? I know that's very weird, right?
Getting a lot of disconcerting looks. I'd really like to sort of unpack. This is, let's do the thumbs up. Give me a thumbs up if we shall proceed. Okay, so you're just bored. You're not disconcerted.